In this video, we will discuss enolates as well as enols as nucleophiles in substitution reactions, and specifically the SN2. Our goals for today are to identify the thermodynamic and kinetic enolates for a given ketone. This should be review. To predict the products of alpha halogenation and alpha alkylation for a ketone. So we're going to learn some new reactions. And in addition to predicting the products, we'd like to propose complete curved error mechanisms for both of those reactions.
Now, hopefully you went and reviewed the enol keto tautomerization and other information about enols, enolates, alpha carbons, all that fun stuff in the review video that I posted. And now that you have done that, you are ready to think about new and exciting reactions to enols and enolates. So why are we talking about this right now? Well, here's some topics that we've discussed recently, and all of them are relevant to the reactions that we're going to discuss today. Ketones are acidic, and they have a pKa of about 20 for the alpha carbon hydrogen, and they can be deprotonated to generate an enolate. Now, enolates, look at the next point, they're basic, and they can undergo proton transfer reactions. They're also nucleophilic, and they can undergo substitution reactions. And what is super cool is they're going to undergo substitution reactions at carbon. They're going to undergo nucleophilic substitution reactions at carbon. And we can understand that through the minor resonance structure for an enolate that shows that they're electron-rich at carbon. And then finally, enolates are alkene-like, so we can apply the principles of alkene stability.
Now I'd like to draw your attention back to this enolates are nucleophilic point. Because they're nucleophilic, we're going to be able to use them in substitution reactions. So go ahead and see if you can fill in a picture of a generic substitution reaction, how you think an enolate might behave in a substitution reaction, particularly SN2. And then go ahead and answer that question. Okay, pause. In a generic SN2 reaction, we have an electron-rich nucleophile attacking an electron-poor electrophile. So what we have occurring is a nucleophile donates its non-bonding pair of electrons to sigma star CX. That generates a new bond and a leaving group. Now, and let's just recall one thing. So we need to have a good nucleophile. Recall two things. So we need to think about, we need a good nucleophile, and nucleophilicity is measured, and we are familiar with the trends in nucleophilicity. We need a primary or methyl halide for a fast SN2. And then finally, we need a stable base as the leaving group. Now, how might enolates participate in SN2 reactions? Well, they would participate in place of the electron-rich species. Enolates and enols, they are electron-rich. They're nucleophilic. So we could expect maybe an enolate to react with some alkyl halide or other electron-poor species in the way diagrammed here. One thing that might confuse you if you're really on top of FMO analysis is that PiCC is it is lower energy than non-bonding electrons on oxygen. So I know like that seems weird, but this is what happens, and it's more complicated than what I've taught you. And this is an example of where that breaks down. So don't worry about it too much. I know that's a really unsatisfying thing for me to say, but try not to worry about it too much. Okay, and so I want to draw out the substitution product. There's the new bond that we've made in this example. All right, I have squeezed in here. Enols are also nucleophiles, although I showed here an enolate, right? So enols are also nucleophiles, but they're weaker than enolates. How can we rationalize that? Well, we've said that the enolates and enols are reacting as electron-rich species, The enolate is just more electron rich, right? It has that negative formal charge. It is more electron rich than the enol. Okay, let's get to it. So we're going to propose a complete curved arrow mechanism for this reaction, which is called an alpha halogenation. And we're going to explain why the observed rate law is this. Oh, where the acid source is acetic acid. So I need to point out a few things to you. So I need to point out that this is a substitution reaction. So here's the alpha carbon. We're replacing hydrogen for iodine. Acetic acid here, this is ACOH. Let's write it out. So ACOH, that's acetic acid. Looks like this. Okay, so it's an acid, which I think we get by the name. So we know we need to break this bond. We need to make this bond. This is going to happen via the enol. It happens via the enol because we are under acidic conditions. Plus, this is not a nucleophile. So you need to make it a nucleophile. And then you have two choices. You're going to make it the enol or the enolate. We're under acidic conditions. It's going to be the enol. Cool. So when we're making the enol, the first step is to protonate. So we will protonate to generate the following species. So we have here a protonated ketone, and the pKa of a protonated ketone is about -2. So this is really, really acidic. Remember what we're wanting to do here. We're wanting to show a substitution on the alpha carbon. So instead of going backwards and deprotonating at oxygen, we're going to deprotonate at carbon. So we need a base. So what base do you think we should use to deprotonate at carbon? Yeah, we just made acetate. So when we deprotonated acetic acid, we generated acetate. So we'll use that as a base because we don't really have any other choice. So we're going to deprotonate, make the double bond, push the lone pair up onto oxygen. So this is another proton transfer reaction. We've generated the enol, which is nucleophilic. And specifically, it is nucleophilic at the alpha carbon. So what electrophiles do we have? Well, we have iodine, and iodine is certainly an electrophile. It's an electron-poor species. What is its LUMO? What is its acceptor orbital? Yes, the acceptor orbital will be sigma star II. And that's a good LUMO. So what we're going to have happen here is we're going to have the alpha carbon attack. It's attacking sigma star II. But when we do that, we also need to reform that nice, strong carbon-oxygen double bond. So when you attack so let's go in order. So form the nice, strong, I call this a lone pair push. Form your nice, strong carbon-oxygen double bond. These electrons from the enol come and attack sigma star II. Fills sigma star, you break sigma. That generates this protonated ketone intermediate. And that's an SN2 reaction, right? And the protonated ketone is not isoluble, meaning that it's really acidic. So what's going to happen now is it's going to be deprotonated. So let's see, do we have anything to deprotonate it with? Not really. So what we're going to use is just another molecule of starting material. So why am I not using I- to deprotonate it? Yeah, because I minus is not a base. Like it's a really, really weak base. So just use another molecule of the ketone and that'll get you to the product and it'll also get you to to another protonated carbonyl that can just keep reacting. So then that will form the enol. So it just keeps reacting. Okay, we got it. So we got our alpha halogenated product. So to summarize here, when you treat a ketone with a halogen, so let's write this at the top. So we have a ketone, and we'll use a simple one, plus a halogen, X2, but it could be iodine, bromine, chlorine. Under acidic conditions, you will obtain an alpha halogenated product, which is called an alpha haloketone. So this is the entry for your reaction chart. Now that you probably ought to pause and ponder, and once you have, let's predict the product of this reaction. This starting compound is an asymmetric ketone, where it has two different alpha carbons. It has a secondary alpha carbon and a tertiary alpha carbon. It's being treated with a halogen and an acid catalyst. So we know that we will obtain an alpha haloketone. The only question really is which alpha haloketone, because there are those two alpha carbons. So we might observe, and let's use bromine. We might observe bromination at the tertiary alpha carbon, or we might observe bromination at the secondary alpha carbon. So which one is it? Well, we need to think about what enols these come from. So the tertiary product comes from that enol. The secondary product comes from this enol. Which of these enols do you think is observed? Yes, it's this enol. This enol is tetrasubstituted versus a trisubstituted one, two, so sorry. It's one, two, three substituents and a hydrogen, so trisubstituted. And tetrasubstituted an enol will be a lower energy intermediate. So in fact, this alpha haloketone is the major product observed. Now, this reaction seems interesting. It might seem random. I don't know how it seems to you, but I will tell you, these compounds are very, very useful. So let's imagine that we just took acetone. Let's make it simple for a second. And we treated it with bromine, with an acid around. So we would have our alpha halogenation, means you're installing a halogen, not the alpha carbon, and this is happening to form this alpha haloketone. Now, how did this work? Because this alpha carbon started out nucleophilic. What have you done to it now? Well, you've made it an electrophile. That's an alkyl halide. It's a fancy, fancy alkyl halide, right? And so you can take this fancy alkyl halide and you could treat it with some nucleophile. For example, you could treat it with cyanide. Cyanide could react in an SN2 reaction. And now you've made this alpha cyano-ketone, where you've made this carbon-carbon bond. So this is cool because these are now SN2 substrates. These are fancy alkyl halides. They're SN2 substrates. So you took a ketone, you turned a nucleophilic carbon into an electrophilic carbon, and then the whole world of SN2 opens up for you. Very cool. Our worlds are colliding right now. We're going to take it up a notch. We're going to look at the mechanism of alpha halogenation under basic conditions. This time, instead of acetic acid, we're treating with a base, with sodium hydroxide. And we are observing a different product. So we're observing a product where all of the alpha CHs have been substituted with bromines. So every single alpha hydrogen, there were 3 of them, we had substitution in all 3 positions. It doesn't matter which alpha hydrogen you deprotonate first. All of them will be deprotonated eventually. But I suppose we will deprotonate first the one that leads to the lowest energy enolate, which is the most substituted enolate. So we observe the enolate here. Enolates are electron rich, and we want to look for an electron poor species for it to react with. And also keep in mind, we are making that carbon-bromine bond at the alpha carbon. So the electrophile is bromine. Bromine is the electrophilic species. And it's going to react through sigma star BRBR. The nucleophile, the enolate, will reform that strong CO double bond. Fancy arrow, let's redo that. And then attack from the alpha carbon. So from the alpha carbon, attack sigma star BRBR. That breaks this bromine-bromine bond. That generates an alpha bromoketone, just like we observed in the previous reaction. And of course, bromide leaving group. So this is an SN2 reaction. And bromide is a leaving group. And so here we have this alpha bromoketone, the substitution product. Excellent. Now, from here, this reaction doesn't stop. If this were under acidic conditions, so if we imagined that this same ketone was treated with bromine, but under acidic conditions, the reaction would stop here. It would stop at just alpha halogenation of the most substituted alpha carbon. But in this case, this intermediate continues reacting. And that's because alpha bromoketones are even more acidic than the starting ketone. Bromine is an electron withdrawing group. It's a halogen. It's electronegative. It's pulling electron density through the sigma framework. That is going to stabilize the conjugate base. That will stabilize the enolate. And so it makes the acid more acidic. So this is even more acidic. You cannot stop it from reacting. This is not something that we can prevent. It's even more reactive than starting material that hasn't reacted yet. Okay, so now we have another enolate, which is electron rich. What do you think that this species is going to do? Yes, it's going to react with another molecule of bromine. Bromine is the electron poor species. So there should be excess bromine here since it's going to react 3 times. That's the electron poor species. In other words, the electrophile. And we will have the strong CO double bond reform. These electrons attack sigma star BRBR. That will generate the product of substitution of 2 of the alpha hydrogens. So we have 2 of those alpha hydrogens substituted now. And then we have just one more bond that undergoes substitution. So I'm going to let you try that on your own. If this were an exam, you would need to write out every step, but I have faith that you can. Just repeat what I have already shown you for the first two substitutions. All right, so when you have alpha halogenation under basic conditions, this is the key. All of the alpha CH bonds are substituted for the halogen. So now that we understand alpha halogenation under acidic conditions and under basic conditions, you should predict the products of these reactions. Hopefully you've paused. So we have a symmetrical ketone where the two alpha carbons are the same. We have X2 and we're under acidic conditions. So this tells me that we will observe a single alpha halogenation, typically at the most acidic or at the most substituted of the alpha carbons. But for this molecule, again, the alpha carbons are the same, so just pick one of them. Now we have that same symmetrical ketone. These alpha carbons are equivalent. There's a mirror plane of symmetry that splits this molecule in half. We're again treating with X2, but this time base. So we know that instead of the product being an alpha haloketone at just the most substituted carbon, we're going to have a fully substituted haloketone. So all four alpha carbons are replaced with, the hydrogens are replaced with bromine. All right, that looks like it kills bugs. Moving along, we're going to look at a symmetric or asymmetric ketone. There are two alpha carbons this time that are different. And alpha prime is more substituted. This reaction occurs under acidic conditions. So we're going to have a single halogenation to form the alpha haloketone at the most substituted of the alpha carbons. That would be alpha prime. So we would expect to see iodine incorporated at alpha prime. And then finally, under basic conditions, we expect to see a fully substituted product. There are three different alpha hydrogens here, and all three of them will be replaced with chlorine. Because every time an alpha hydrogen is substituted for chlorine, it makes that alpha carbon even more acidic. So after the first substitution, the pKi has gone down. So this is even more acidic, so the second substitution happens, and so on and so forth. So under acidic conditions, you are going to substitute the most substituted carbon for one halogen. So one of those CHs for one halogen. And most substituted alpha carbon, I should be clear. Under basic conditions, both alpha carbons, all of the alpha CHs are substituted. So what should you put on your reaction chart? Yes, alpha halogenation under acidic and basic conditions. So go ahead and write that out so you can make sure you remember and you can compare with me. Now is a really good time for us to pause and think about our synthetic toolbox. So our synthetic toolbox, it contains the reagents and the strategies that we know for synthesizing or making molecules. Right now, the big group of molecules that we learned how to make were ethers, and we thought about disconnecting the CO bonds. We knew that we could make ethers by SN1 or by SN2, and believe it or not, we're going to even learn some more ways to make ethers later next week. So we're going to be making all kinds of functional groups, not just ethers. So you should pause and think about what groups of electrophiles you know, what groups of nucleophiles you know, and how you're going to figure out if something is an electrophile, nucleophile, acid, or base when you don't know anything about it. Now, groups of electrophiles, well, you've just learned a new one. You've learned halogens. And then you should know that alkyl halides are electrophiles. Any other electrophiles that you thought of? You could use alkyl tosylates, you know them as well. They're equivalent to alkyl halides. What groups of nucleophiles? You know so many nucleophiles. But let's group them into non-bonding electrons on a heteroatom. But in that group, you could have a neutral, so you could have an alcohol, you could have a negative formal charge, such as an alkoxide. Other nucleophiles, well, we've now learned about enolates and enols. And I said that pi electrons were reacting here. Okay, and we're going to learn more and more types of nucleophiles and electrophiles as we go on. And then make sure you don't skip this question. This is one I need you to think about on your own. So now that we've thought about that, big hint, what other electrophiles might enolates be able to react with? Well, we only listed two. We listed two. We listed halogens and we listed alkyl halides and tosylates. So can they react with alkyl halides and tosylates? Yes, indeed, they can. So we can imagine, and I believe I diagrammed this when we first began this discussion. We can imagine enolates reacting in an SN2 reaction. Oops, we are not losing the R group, right? We're losing X. And when they react in this SN2 reaction, not only do you reform that strong CO double bond, and you do get a substitution product, you've made a carbon-carbon bond. When we think about our synthetic toolbox, what types of molecules will we be making? We'll be making molecules with lots of carbon in them because carbon is the building block of organic compounds. So when you make a carbon-carbon bond, that's a particularly important reaction. So we're going to think more now. Oh, and here you're going to love this. So alpha carbon and alpha carbon. Ha, okay. So this reaction that we just diagrammed out in a generic format is called alpha alkylation. We'll be adding alkyl groups to the alpha carbon of an enolate. Now it's your turn. See if you can propose reagents, specific reagents, to accomplish this transformation. This is the bond that we are proposing to make between the alpha carbon and carbon 1, as I've labeled it here. That bond can be made from an enolate nucleophile and an alkyl halide electrophile, and this will occur in a substitution reaction, as we've been discussing, so an SN2 reaction. Again, the alkyl halide needs to be a good SN2 substrate, which it is, it's primary. The leaving group could be any of these. It could be an alkyl halide or an alkyl tosylate. And I am choosing to use the enolate because enolates are better nucleophiles than enols. Now, we know that we need to do two things. We need to generate the enolate, and then we need to treat with the electrophile. Well, how do we generate enolates? Yes, we're going to treat with some base. So what sorts of bases might we use? All right, I'm going to guess you're saying hydroxide. So you want to, you like to use hydroxide, and then you're going to we're treating with our electrophile. All right, so we'll have the base. Let's just write this out. Sorry, I got excited here. So we're going to have sodium hydroxide, and then we're going to treat it with ethyl bromide. Okay, is that going to work? Although it was a good idea, no, it is not going to work. The reagents here will react with one another in SN2 and E2 fashions to generate undesired byproducts. There will be zero, absolutely no alkylation of the alpha carbon. Now, how can we slow down or avoid the reaction between this nice reactive primary alkyl halide, an excellent SN2 substrate, and hydroxide, which will do an SN2 or will also participate in an E2 reaction with this alkyl halide. I've indicated the beta hydrogen. Now, to avoid it, perhaps we can use a bulkier base that will not be as reactive in an SN2 reaction. So what am I referring to? Yes, I am referring to sodium hydroxide. I'm referring to sodium T-butoxide. It is too bulky for a fast SN2. So might this work? Might this allow us to generate the enolate? And then the enolate, as an electron-rich species, can react with the electron-poor species to generate the desired product. Well, good question. It's a good idea. Let's keep thinking about it. And I want to think more deeply about this proton transfer reaction. Let's consider this proton transfer reaction. Go ahead now, pause, and complete the reaction, calculate the KEQ, add the curved arrows, all of that yourself. All right, we have acetone here, which is a symmetrical ketone. The alpha carbons are exactly the same. The alpha carbon is the acidic position for a ketone. We know that the pKa is going to be about 20. Why? Because you have memorized it. It was not on our original list of pKas you memorized, but after today, it is. Okay, we're going to deprotonate at this alpha carbon and generate the enolate. We directly go to the most stable resonance structure of the enolate. Why? Well, because that resonance structure most represents what it looks like, and because I asked you to. Two great reasons. So we have the enolate. This is the conjugate base. T-butoxide is the base on the left side of the equation. Then we end up with this new OH bond. And we have T-butanol. All right, now how do we calculate the equilibrium constant? Yes, we're going to calculate the equilibrium constant. It's 10 to the difference in the pKa between the product acid and the reactant acid. So the pKa of the product acid minus the pKa of the reactant acid. In this case, the ketone has a pKa of 20. Alcohols have a pKa of 16. So the equilibrium constant is 10 to the 16 minus 20, or 10 to the negative 4. So what does that tell us? It tells us that this side of the equation, the left side, is favored at equilibrium. Now, that's not necessarily a deal breaker. Because, even though only a little bit of enolate is favored at equilibrium, if this goes on and reacts with some electrophile, such as, an alkyl halide, that will drive this equilibrium by Le Chatelier's principle. So this, in theory, could be okay. But I have to tell you, this doesn't work very well. For enolates to act as nucleophiles with alkyl halides, you really do need to quantitatively generate them, meaning you need an equilibrium constant greater than 1. So the problem here really is the base. The base was the problem for both of our ideas. Sodium hydroxide was the problem, and now sodium T-butoxide is the problem. And it really is just that. Alkoxides are not basic enough to completely generate the enolate. So let's think about a new base. That base is called lithium diisopropyl amide, aka LDA. So lithium diisopropyl amide. And I need to be very clear about something with you. I do not want you to start using this base all the time. This base is very strong. We'll talk about it in a second. And it's only to be used in very specific contexts. And what I'm about to show you is an appropriate context. So do not start randomly using it. You only use it in the context that I have shown you. So lithium diisopropyl amide, LDA, and it is a deprotonated amine, right? So let's look at its reaction with acetone. So I've drawn acetone out. Lithium diisopropyl amide would deprotonate the alpha carbon in a proton transfer reaction. The electrons in sigma CH then make a pi bond between the alpha carbon and the carbonyl carbon, and those electrons in the pi bond go up to oxygen. We go directly to the most stable resonance structure of the enolate. We can do it. I have faith in you. Now, to analyze the proton transfer reaction, we need to look at the pKa's of the product acid and the reactant acid. So what do we see? Well, the product acid is an amine, right? It's an amine. So what is the starting place for a pKa of an amine? What do we memorize for that functional group? Yes, you memorize 35. So the pKa for this reaction will be, the equilibrium constant for this reaction will be about 10 to the power of 35 minus 20, or whoa, 10 to the 15. So is this reaction favor products or reactants at equilibrium? Yes, products. Super favors products. We will see quantitative 100% essentially deprotonation to form the enolate. So we can get 100% enolate by using LDA. And what we've done here is we've just used a much, much stronger base. We just investigated the deprotonation of acetone with LDA to 100% make the enolate. The equilibrium constant was quite large. It's 10 to the 15. Now, acetone is an example of a symmetrical ketone where the alpha carbons are exactly the same. But we can think about what would happen if we had a ketone with two different alpha carbons. And we know that under thermodynamic conditions, such as if you had an alkoxide base, you would observe the thermodynamic enolate, the most stable enolate. For LDA, you actually observe what's called the kinetic enolate. And that is because LDA is bulky. It has those two large isopropyl groups on it. It is a bulky base. There are steric considerations for the energy of the transition state of this deprotonation. And it's very difficult for LDA to get in to deprotonate the proton that leads to the thermodynamic enolate. So instead, LDA favors deprotonation of the least sterically hindered alpha carbon. So in the case of the asymmetrical ketone at the bottom of the screen, we will observe deprotonation at the primary alpha carbon. So LDA will actually deprotonate the primary alpha carbon to generate this enolate, the kinetic enolate. So with LDA, we observe the kinetic enolate, 100%. It's a quantitative deprotonation. So we observe that kinetic enolate. Just put the equilibrium constant is much, much greater than 1. Now, if we used an alkoxide base, or if we use hydroxide instead of butoxide, we would observe the thermodynamic enolate, and of course, the equilibrium constant for this reaction would be less than 1, but that's not the point here. The point here is that LDA is huge, absolutely huge. and it deprotonates the least sterically hindered proton. Okay, so let's make sure we have this. With LDA, we make the kinetic enolate. A couple things before we moved on. I just glossed over this minus 78 thing. This is the temperature at which these deprotonations have to take place. I mean, LDA is very reactive, as I mentioned, and this temperature, negative 78 degrees Celsius, is required just to because reactions are very exothermic, so it's required to control the heat that's associated with these reactions. And you have a reaction at minus 78 by making what's called a dry ice and acetone bath. So when you make an ice bath, you're used to using solid water and liquid water, and that gets you to 0. But to get to negative 78, you use acetone, liquid acetone, and dry ice. You just put your reaction in there, and it will be at negative 78. Okay, so you have to have this temperature whenever you use LDA. Okay, I'm about to confuse things a little bit, so just make sure that you're solid here. You understand the kinetic enolate is the less substituted one. Thermodynamic is the more substituted one. If you use LDA, it's super big. It makes the kinetic enolate. If you use an alkoxide or hydroxide, you get the thermodynamic enolate, but the equilibrium constant will be less than 1, and that's not super. And because that's not super, because I mentioned to you, we really need just 100% of the enolate in order to react with alkyl halides. There's a clever way around this. There's a clever way to use LDA but still get the thermodynamic enolate. So I know that's confusing, so let's just take a step back. So if you want to make the kinetic enolate, you want to do a normal use of LDA. What I'm going to have you do is I'm going to have you use just a little bit more than an equivalent. So you can see I used 1.05 equivalents of LDA. So it's just a little bit more than 1 equivalent, which means 1-to-1 base to ketone. And that is just to ensure, so that just ensures that there's no unreacted ketone around. Just ensures that all of the ketone is deprotonated when you have just a little bit more than 1 equivalent. All right, so that's just the normal use of LDA, exactly what we were talking about right here. I just didn't mention that equivalent thing. Now, remember what I said, which is that you really need to just 100% make this, because then you can take it once you have it in a bottle and you can treat it with your alkyl halide and you can get an SN2 reaction. Because I think we kind of forgot that was sort of the entire point of this discussion, was making these bonds between the alpha carbons and alkyl halides. So once you have this enolate, you can react it with the alkyl halide. The alkyl halide never has to see the base, so there's not going to be any of that SN2 or E2 or any of the issues we were talking about here. So because it's nice to have an equilibrium constant way greater than 1 to totally make the enolate, we would like to use LDA to also make the thermodynamic enolate. The thermodynamic enolate for this asymmetric ketone is this one, where you deprotonate the more substituted carbons. So we have this tetra-substituted alkene versus tri-substituted alkene. Tetra is more stable. All right, how does this work? I know it's confusing. So what happens is LDA deprotonates to make the kinetic enolate first. So you see I've used just less than 1 equivalent. Man, I'm not using my mathematical signs well. Just more, just less than 1 equivalent. So what that means is I'll get 95% of the kinetic enolate, and then I'm going to have 5% of the unreacted starting material. And guess what? Enolates are bases. Ketones are a little bit acidic. At what carbon? Yeah, at their alpha carbon, that's the entire point. And so this little bit, this little 5%, it donates its proton to the kinetic enolate. And then what happens is that and so it gets deprotonated here. And so it establishes equilibrium. So you have this reacts, this acts as the acid, this acts as the base. It establishes an equilibrium until all of the enolate isomerizes to the thermodynamic enolate. That's pretty cool. So we can use LDA to get both enolates. Now, I will say in your textbook, when the thermodynamic enolate is required, the author uses potassium T-butoxide. And you can do that if you want, but it doesn't work in real life. And I honestly think it's just more confusing to tell you it does when it doesn't. So if you need the thermodynamic enolate in order to do an alpha alkylation, you just use a little bit less than 1 equivalent of LDA. So what are the conditions necessary to make each of these enolates below? You go ahead and pause and try. These are all asymmetrical ketones, so you're going to have to make some choices. We can see that the products are constitutional isomers of one another. The first product comes from deprotonating here. The second product from deprotonating at the other alpha carbon. We would describe the first product as the thermodynamic product because it's tetra-substituted. The bottom product is the kinetic product. It's a little bit higher energy. So it's the tri-substituted. So less substituted means it's a little less stable. It's a little bit higher energy than the tetra. But it was easier to deprotonate. It was easier for LDA to get in there and deprotonate the less substituted alpha carbon. I guess I gave away what happens, right? So this is just classic use of LDA. So to make the kinetic enolate, you would use LDA. And if you want, you can say a little bit more than 1 equivalent, and you do that at negative 78 degrees Celsius. You always need to have the temperature with LDA. To make the thermodynamic enolate, I've given you 2 choices. You can use a little bit less than 1 equivalent of LDA, and that, like I said, it first makes the kinetic enolate, but there's a little bit of the enol or the unreacted ketone left over, and that acidic alpha carbon allows for equilibration to generate the thermodynamic enolate. And that's how I want you to do it if you need to use the thermoenolate in like an alpha alkylation. I'm going to show you in a second. So you could do this with LDA and negative 78 degrees Celsius, or you could use potassium T-butoxide, but just understand if you do that, your equilibrium constant is less than 1. What is the point of this? Well, the point is if you can make 2 different enolates, that means you can make 2 different alpha alkylated products. So if we take the enolate here and we treat it, the thermodynamic enolate, and we treat it with an alkyl halide that is a good SN2 substrate, the thermodynamic enolate will be alkylated to generate a product like this, okay, whatever the R group is, and this would be a racemic mixture. And if we took the kinetic enolate and we treated it with the same alkyl halide, this can undergo an SN2 just as before and generate the constitutional isomer, which would look like this, and that would probably be a mixture of diastereomers, a big mess, but we'll just put plus minus here. Okay, so we have these isomeric products. And you'll see our goal as we move forward in this class is to be able to make absolutely anything. So we want to make this, we alkylate the thermodynamic enolate. Want to make this, alkylate the kinetic enolate. All right, and this reaction, this SN2 reaction here, between the enolate and the alkyl halide, this is called an alpha alkylation because they're alkylating the alpha carbon of the ketone as the enolate. And again, it is best done with these lithium enolates that you have quantitatively 100% generated using LDA with that large equilibrium constant that we discussed on this slide. Okay, you try. Let's predict the products of these reactions. So we see we have LDA, and this is a base. We'll be deprotonating the alpha carbon. We have a little bit less than one equivalent. So that means, okay, this is how we're making the thermodynamic enolate. Again, LDA initially makes the kinetic, but when you use less than an equivalent, it will equilibrate into the thermodynamic enolate. So after step one, and we're just going to go ahead and draw it out. Usually you would just draw the product of both reactions here. Well, here, we'll do it underneath. So after step one, you would have the thermodynamic, more substituted enolate, the lower energy enolate. And then you treat it with the alkyl halide. So that's going to undergo an SN2 on the alkyl halide. And now I want you to be really, really careful here. Number your carbons. Make sure that you don't lose any carbons. And try to draw the product before I show you. There we go. And this will be a racemic mixture. Okay, I'm not gonna number, I'll highlight, but there's those 3 carbons. And then here's that alpha carbon of our enolate. We'll call that, yeah, we'll just call it alpha. All right. So in this second reaction, we have LDA again. So we know that we're making an enolate. And let's go ahead and look at our 2 alpha carbons. But this time it says that it's 1.05 equivalent. So this is just normal use of LDA to make the kinetic enolate, no confusion whatsoever. So let's draw out the kinetic enolate. The kinetic enolate results from deprotonation at the less sterically hindered alpha carbon, that is alpha prime. And then from here, that enolate will do an SN2 once it's treated with the alkyl halide to generate the alpha alkylated product. Again, don't lose any carbons. Here, this is the bond we made in the first reaction. This is the bond we made in this reaction. Here's your alpha carbon. Here are the 3 carbons of the alkyl bromide. All right. So you see the 2 products look pretty different, and you use the same starting ketone. They're different based on which alpha carbon acted as a nucleophile in the SN2 reaction with the allyl bromide, and you control that by making the kinetic or the thermodynamic enolate. This is a very important reaction. We've made a carbon-carbon bond, so very exciting. You've learned a lot. You really should reflect on what you've learned and what questions that you still have. Make sure that you keep up with your reaction chart. Okay, can you identify the thermodynamic enolate for a given ketone? Yes, it is the more substituted one. So for example, if we have, let's look at something new. All right, let's say we have, this is not new. I tried, I'm sorry. We have this ketone. There are 2 possible enolates. There is this enolate And this enolate. The more substituted double bond, this double bond has 1, 2, 3, 4 substituents, whereas this one has 1, 2. The more substituted one, this is the thermodynamic, the more stable enolate. And we're thinking about double bond stability. But the di-substituted one, the other here, it's the kinetic. It's just easier to make it. It's easier to deprotonate it. And what I mean by that is there's a lower activation barrier when you're using a bulky base. There's just a lower activation barrier to deprotonating that proton. Okay, so we've achieved those two goals. Excellent. Predict the products of alpha halogenation and alpha alkylation for a ketone. We can totally do that. Let's just keep it with that same ketone. Okay, alpha halogenation. So that was some halogen. We'll do X2. And then we could have some acid catalyst or some acid, or we could have some base. Under acidic conditions, there's a single halogenation at the more substituted alpha carbon because it goes via the thermo-enol. And then under basic conditions, you will have halogenation at all because after that first reaction, then it's more acidic, so it keeps going. Okay. All right, now what else? Alpha alkylation. So you could do just a little bit more than one equivalent of LDA. It will go via the kinetic enolate, and you'll get alpha alkylation at the less substituted of the two alpha carbons. Or you could imagine using just a little bit less than one equivalent of LDA. What this does is it allows you to use your alkyl halide in a separate step, but because you've used less than an equivalent, it does equilibrate to the thermodynamic enolate. So you'll get substitution at the more sterically hindered carbon. And so this time that's the carbon-carbon bond that was made. And that's great because we can make two different isomeric products in a pretty similar fashion. Okay, and curved arrow mechanisms. Yes, you can do it. I know you can. All right, ready, set, go practice.